All right, welcome everyone. Hey, Parisa.
Hi, how are you doing?
Okay, so let me just share. Is everyone seeing my slides?
Yes.
All right, welcome to Neuro-Symbolic Wednesdays. Once again, today we have the pleasure of hosting Parisa, and Parisa is doing many things with the Institute, including being on our education committee. So, and you'll be hearing about that soon. And today she's going to tell us about, I think, a very good way to get into Neurosymbolic is to know some of the big frameworks. And Luis hinted at some of them last week, and Preeta is going to go into more depth today. And I think this is how you can quickly answer the question, roughly, what is Neurosymbolic AI? It's a good part of it. You can read much more about Parisa. We'll put these slides out, but many words and highlights. The questions and comments are 3 different places. You can enter those, and wherever you enter them, they will come to us, and Olga will find them, and we'll read them in the chat or in the session. Just in general, these are all the different ways to connect with us. We do all of them if you want to be maximally connected. The most important one is Discord. Get on Discord. This is where the community lives, and all information will eventually go there, including things like slides after the fact, and you can ask questions there and so on. Okay, and this learning site is what we're working on with Provita, and you'll be seeing that soon. Different ways to participate, you'll see on this page at the bottom. Okay, and just a hint, so this will be our last talk of the year, so I want to thank everyone in advance for being with us so far. We're going to take a break of a few weeks, and then for the holidays, and then Pascal Hitzler is our next speaker, January 7th. All right, January 7th. Just a quick reminder, we are actively putting together a working group on this, our Neuro-Symbolic Agentic protocol. So if you're interested in programming languages, knowledge representation, and anything around agents and systems, this is where a lot of action will be. And I've flashed this before, but these are some of the types of topics. If you want to talk to us about anything, please do. And we're hiring and taking donations and all sorts of things. Maybe this is a time we don't generally talk about it much, but we are a nonprofit, and this being the end of the year, if you want to show some holiday spirit, you like what we're doing, you're concerned about the direction AI is going in, you feel AI needs to be safer, smarter, and slimmer, and we're doing everything we can to get there. Please help us out. It's very easy. It's on the website. On the participate page, you can donate. Okay, that's it. With that, let me pass it over to Parisa.
Thank you so much, Alex. Screen. Do you see my screen? I think it's not in presentation mode. Why is that? Okay. Let me see.
This is how you know this is a live, authentic event.
So now is it?
We have
the slides? No.
we have this right side about slide layout.
I cannot do window. That's weird. Enter screen.
Worst case, Parisa, we can still see your main slide.
how about now? If I do this, do you see the entire? Hello?
No.
Do you see the
No.
movement of the slides?
Yes.
Oh,
Yes, we do.
Good.
Now, is it entire screen?
Yes.
Okay, perfect. Okay. I can start?
Yep. Go ahead.
Okay, perfect. So good morning, good evening, what time zone you are. I hope you have a great time. And thank you very much for Alex for inviting me to give this lecture. This was a bit a short notice, so I was thinking how to organize this stuff. So I was going to... yeah.
Sorry, by the way, Parisa, your camera is off on you.
Oh, okay, I see. Let me see. I think I just took this and now let me do the... Okay. You see not my ideal camera, but you see a camera, right?
We do. Yeah.
I had external camera, but it's not working. Okay. So let me share again.
Hey, okay.
Great. Okay, let me do entire screen. Okay, so yeah, I was thinking to present maybe some work that we did like about 12 years ago about declarative learning-based programming and how we were thinking about designing intelligent systems in a hybrid way, and then grow to neuro-symbolic modeling, or the words and keywords actually change later. But I will touch on different parts of our work that are in the same line of thinking. I hope I could make, I hope my story is coherent. As I mentioned, this was a little bit a short notice for this lecture. So to be just self-contained, the lecture, I start with the definition or adaptation and reasoning that is requirement for intelligent agents, and then also discuss about what is neurosymbolic modeling, why we need genetic frameworks versus just algorithms, looking at this from the application perspective, and then also lightly connecting to the recent LLM-based agentic frameworks. But I didn't have time to work on this extensively to make this connection. Maybe in a future lecture, I can work on this further and have a lecture only on this one. So just to explain this motivation, like we have as an intelligent agent, like if it is human or a machine, we might need to solve problems with our perception or with our reasoning capabilities. For example, in this image, if I tell you point to a bottle of water, you might immediately point to here or to here, and you don't need to do a lot of thinking. Or if I tell you point to the man with the green shirt, you can immediately recognize it without even thinking. But how about this query here? How many water containers in front of the human who is sitting left of the another human holding the microphone? So for answering this question, you might need to see where are the microphones, like look at the microphones and detect them. Then look at like the human that holds the microphone. And then you might think, okay, now the human sitting left of the person who holding the microphone is this one. And now you need to do counting how many water containers are in front of this person. And you can find out the answer. I'm not sure how many seconds it took you to solve this problem, but I'm sure you cannot just like answer this by just one look. You have to really look at the relations, object relations, and do the counting to be able to answer this question. And the current neural models, actually the state-of-the-art large language models, all of them kind of failing to answer these questions being wrong in different ways. Also, like similar question, if I ask you how many people are in this picture, I won't trust you if you just tell me this in less than 1 second, because I really need you to count. I don't think that we can just look at the volume of the people and do an estimate based on perception. We really need to do reasoning, where by reasoning here, it's explicit counting and detecting these people and counting the number of people that are in this image. So we have different types of reasoning that classical AI has been looking into, like deductive reasoning, abductive reasoning, common sense reasoning. So I don't go to the details of this, but I just want to give an example for the people who don't have a background. For example, deductive reasoning is kind of something that many like classical AI logical reasoning systems are touching on. And here is an example of it. Like, all triangles are red, all circles are blue. The hidden shape is a triangle. What color is the hidden shape? So you know that the hidden shape is triangle, then you know that all triangles are red, then you know that the color of hidden shape should be red. So this is deductive reasoning. Now the question is that, should we do this kind of reasoning in a neural way or a symbolic way? Neural way means, okay, pass these pixels to the model, or pass this text, raw data to the model, and the model will do this forward neural computations and give you an answer. That is a neural way of doing it. Symbolic means really spell out the symbolic logic. Red X, blue X, if X is red, if X is triangle, then X will be red, and so on, and then do entailment, logical entailment to solve the problem. So, but I mean, we can say that both neural and symbolic models will be able to solve this to some extent. Neural models to some extent, because we are never sure what kind of reasoning steps are taken. The model perceives something and does distributed computations in the continuous space, gives you some answer. Symbolic reasoning, we actually see the concept, we map the sentences or images to symbols, we have the rules, and we can do explicit reasoning. But then there is advantages and disadvantages, right? Again, like symbolic reasoning, we know what's happening, we know exactly what rules applies, and we can see how the model reasons. With neural models, we cannot see that. And also, the process of reasoning is more robust and reliable. You know always this is the process. With neural modeling, again, you don't know. That's why the model can go wrong and we cannot trust it. So the type of reasoning describes what kind of inferences is being made. Like the implementation of reasoning can be done in a symbolic or neural way, but actually many modern AI systems are going towards the hybrid systems, I argue. For example, you can look at alpha geometry. You want to do geometrical reasoning, the neural model can generate like possible kind of hypotheses or possible rules that needs to be applied to a specific situation, but the actual reasoning is done symbolically by explicitly applying these geometric rules. In this way, you can do like optimize the search space or the efficiency of the symbolic reasoning. You can also do the actual symbolic reasoning, which is explainable and reliable. So again, going back to this issue of like, okay, we need complex reasoning depending on the task, and neural models are not reliable in doing this. We need the combination of these paradigms. So I'm going to argue that, okay, for designing complex intelligence systems, we need to have this both perception and reasoning, or what is so-called thinking fast and thinking slow capabilities. We need to have various levels of abstractions for reasoning. We can use models that actually learn neural patterns, and then we can do explicit reasoning on these neural patterns to learn their compositions or infer information about their compositions. However, models need to handle basic concepts, relations, types of relations, and be able to compose them. So the concepts can be learned, like the perception level concepts can be learned, but for generalization, we need to be explicit about reasoning. Like again, back to this image that I showed you. We need to learn in that specific context. We need to learn, detect objects, detect the left-right relationships, but then we need to put them together and then do counting to be able to answer the question in a more generalizable and explainable way. We can also say that, okay, thinking fast or neural modeling, these are kind of manifestation of this. Thinking fast could be neural modeling, that you just do forward computations, and the manifestation of slow system thinking can be, or system 1 and system 2 also, I'm sure everybody here has heard about it, is kind of search-based or classical AI-based kind of techniques for searching, explicit searching for finding the best solutions. And we need the combination of the two. Now, I'm going to highlight this, like from one specific perspective, I'm going to highlight the gap. And that perspective is like, if we want to design these hybrid models, what is the gap? So what is the gap for designing what I call integrative AI frameworks that integrate both kind of modeling? Are there any tools and libraries for this hybrid modeling? That is a question. And what are the components of this hybrid modeling? What the tools that are supposed to do this hybrid modeling? What components they need to have and how they work? And the last question, what kind of supports are we expect from these tools? So this is again based on, I mean, as I mentioned, this is based on some studies that I did like kind of 10 years ago about this. It was more about like learning-based programming, programming paradigm that we can do composition of components that are learning-based. We can integrate the knowledge. So we called it learning-based programming. Now I think it is very relevant to what we call now neurosymbolic modeling. In these modeling paradigms or frameworks, we want to learn from the data in a neural way. So we have the component of data, but then we want to have this structure of the data model. So we need to model structure. Of course, we have continuous representations, but we also need to have, as I mentioned, entities, relationships, so graphs. We need to model the structure, but we have learning from the data as well. So this one component is the data. And for the hybrid paradigm, we need to have both representation in continuous space and representations in discrete space to be able to learn and do reasoning. We have the symbolic knowledge as well, like if this, then that. For the explicit reasoning, we need to have a language that represents this symbolic knowledge, and we need engines that are able to do reasoning based on this symbolic knowledge. We need to deal with uncertainty in data and knowledge. Maybe in distributed space, uncertainty is implemented or implicitly or inherent in these representations. But when we're talking about symbolic representations, we have to be clear about how we want to represent uncertainty about the symbols. So we need to deal with that in the framework, in an ideal framework. And we need to do model composition, because we think there are models. One model does object detection, one model does counting, one model does relations. So we need to have a language that helps us to do model composition. Here I mentioned it, I added this sentence just today. This is not an old slide. This is not what I had originally here, like role taking and communication, but this is similar to role taking and communication that happens in the current agentic frameworks. We need to have multiple models that work together, communicate together to be able to solve a complex problem. And then another aspect that also is not very clear to me, but I think it is very important. This is clear from classical AI, what is the difference between data and knowledge. But maybe for the current way of thinking about it in neurosymbolic systems, maybe the definitions are a bit like kind of a bit vague now. How we can transition between what we call data and what we call knowledge, which is higher level and can be used even both symbolically or sub-symbolically. So the transition or the representation of data and knowledge is another thing that the frameworks, hybrid frameworks, need to address. And then another component that we were thinking about at the time, like designing learning and inference paradigms for models and their interplay. So each model can have its own learning from data paradigm, and we might have like different inference algorithms that collect information from different models and inference over them. But if we are thinking about a generic framework, we should be able to actually have different algorithms that provide learning and inference. So finding the right abstraction and primitive for this integrative paradigm, I think, is a challenge. We have seen implementation of these ideas that I'm going to point to you, and you can also think about it nowadays in the era of large language models. People think about agentic frameworks, and I think they are trying to deal with some of these challenges still in the based on the new technologies that we have available. So this is basically the components, summary of the components that I was pointing to in the previous slide. But I also want to point to the classical AI models that have that address this kind of components or challenges. And then in the integrative neurosymbolic frameworks, people think about, okay, now bring this classical AI model and put it together with the neural modeling. But let's have a list here to see what were actually classical models or systems that were dealing with these problems. If we think about data modeling, we have had database management systems and databases with probabilities. We have had probabilistic databases, like we have had deductive databases, like logical reasoning with databases, probabilistic reasoning with databases. This is basically, we have had all these classical AI or data management systems separate even from the AI for dealing with the structured data, that when we talk about symbols, it becomes very relevant. Then we have also knowledge representation and reasoning systems. We have a lot of classical AI systems, program languages that are based on first order logic and provide representation languages and reasoning engines for doing different kinds of reasoning. We have had probabilistic programming languages that, let's say you have random variables, distributions, and you have probabilistic inference algorithms that you can program for those. And then we have had like probabilistic logical programming languages that try to combine logical representation and dealing with uncertainty, like Problog, Prism, and some other languages. Then we had this paradigm of a statistical relational learning that I think members of that community actually now are mostly rebranded as kind of neurosymbolic AI, but these are works like Bayesian logic, Markov logic. K-log was another system that was developed. So there are kind of, the main idea has been to integrate logic with statistical learning and dealing with uncertainty. But now the statistical component becomes more generic and we talk about neural modeling. So basically statistical relational learning becomes statistical learning becomes neural learning, and relational becomes the logical representation or symbolic representations that we talk about in the neurosymbolic systems nowadays. We had this more maybe narrow or niche idea of learning-based programming that was proposed originally by Dan Roth, and I was working on this. He had this learning-based Java. We developed Soul, and the main idea was, again, to have the learning as a pivot of the programming language and get the probabilities from the learning models and design how they can communicate or constrain each other with logic or relational representations. Now we have this agentic framework like AutoGen, LangChain, LangGraph. We have like large language model based frameworks that they try to put backend large language models together, assign roles to them, have their communication modeled in with kind of more a smooth way of agentic programming framework. And I think this is, again, very connected. And maybe this agentic framework, they are not explicit about, okay, how the communication can be made. There is tool calling that could be a kind of symbolic solver. They talk about communication that could be with natural language form or visual form. It could be based on sensory data or formal. They are more generic, but the current status is mostly language models, and medium of communication is mostly input-output sequences that comes in and out to these language models. But I think we can think about neurosymbolic models that can really organize these agentic frameworks by looking into this principle of data modeling, knowledge representation, and so on that I talk about in this new agentic way of doing it. So yeah, that is about neurosymbolic framework already explained. We also have a survey that we try to put all of this in perspective. This is again before actually the rise of and popularity of using large language models at the scale that we see. This was about, again, organizing the studies about combination of statistical learning with logical reasoning and symbolic reasoning. And then we had these application needs that we wanted to highlight. We were thinking about nowadays AI is popular. We do a lot of complex applications. Applications mostly need interaction with heterogeneous data, text, image, audio, video. And there is kind of a lot of domains apply AI. So we have domain expertise and knowledge that needs to be included in the designing of the applications. Again, representing uncertainty, different types of algorithms and model composition and abstractions needs to be used for solving problems from the application perspective. And then you can look at this paper, but there we are trying to look at all these programming paradigms like logical programming, even deep learning libraries like PyTorch, TensorFlow at the time, even structured output prediction models. We put all of them to, in one perspective and try to explain how they deal with this application needs. And then there is another meta kind of perspective that you can see. All of these tools try to write programs for dealing with these application needs. What about actually learning to write these programs? Can we learn architectures, for example, if you're talking about PyTorch kind of library? Can we learn dependency structures if you're talking about probabilistic programming? Can we do program synthesis if you're talking about just procedural differentiable programming and so on? So basically, that might, if you're interested, this might give you a perspective like how we were thinking about hybrid paradigms and the application needs and different levels of programming that needs to address the application needs. So to highlight some of this, as I mentioned, we need to interact with heterogeneous data when we are coming to the complex applications. And then I'm not going to the details of this, but the slides will be available. You can look at these details. But from the messy data, data can be unstructured, can be structured, can be graphs. We want to get representation of the data. This could be distributed representations or symbolic features. We want different types of the high level abstraction. We want to see, okay, I want to program what I want to do, but I'm not going to specify how to do it. I want to abstract away my programming from underlying algorithms. I don't want to write explicitly a lot of low-level algorithmic code. And we also, we were thinking, okay, there are two different types of abstractions. One is based on data and domain, and what is based on computations and algorithmic. To give you more examples, for example, if we think about algorithmic level, maybe if we think about probabilistic programming, then dependency structure of the variables might be kind of algorithmic level abstraction that we can have there. Or when we talk about more domain abstractions, maybe logical representations of saying, okay, I have a people, I have location, I have spatial relations, I have employment relations. So I'm going to have logical representation of the domain. That is kind of the abstraction that I'm going to program. Or some tools might give us the abstraction about the mathematical objective functions. I want to have this loss function or that loss function, and I'm going to program for my actually learning objective. It is a bit lower level, but it can give us another kind of abstraction. With deep learning tools, you actually build your computation graph, you define your loss. So that is basically more or less the abstraction that is provided for the more learning-based tools. We can have a procedural knowledge abstraction and have differentiable program as well in this case. Representing uncertainty, so when there is missing information, uncertainty about data and knowledge, how we can do this. So again, we have different paradigms like statistical and probabilistic models that express this. We can have like probabilistic logical programming, probabilistic programming with probabilistic traces of execution, and differentiable programming that try to address this uncertainty in older studies. We need to cover different algorithms. Is it classical machine learning that you're using? Is that deep learning? Is that language models? We want to actually cover different kind of ranges of algorithms and basically different formalism need to be covered. If we are focusing on a specific formalism, I'm doing probabilistic programming, or I'm doing deep learning, this is easy. I have a set of algorithms that are in that scope. But if I'm going to move in between different systems, like symbolic system, neural systems, then it's hard to unify. It's hard to unify, like to cover different types of algorithms. And model composition is basically building models that do a small task and compose them for doing complex tasks, and how these models are going to interact with them is important. So in general, this is also in modern agentic frameworks, but in this way of neurosymbolic thinking, we are thinking about, okay, specifically if these models, some of them are doing symbolic reasoning, some are reasoning, how we can actually integrate them and what will be the interplay between. And this is also, I want to point to this now talking about or focusing on this symbolic modeling. I wanted to also to point you to this Henry Coe's classification of the different kind of combination of this symbolic sub-symbolic paradigm. So you can have symbolic models, then calling neural models, then passing the output to symbolic, or there could be different configurations. Again, I don't to go to the details, but you can look at Henry Coe's slides, and also we briefly explain this in our paper. So different kind of communication between symbolic is important. And here, for this specific case, I want to argue that if we think about generic frameworks for neurosymbolic, we should be to design different paradigms. It's not, if you have an algorithm, the algorithm might follow this single paradigm of symbolic and neural, or neural and symbolic. But if you're thinking about frameworks, then it means that in the program, I have to be able to design modules and design the way that they interplay. So I want to be a generic framework that gives me the capacity to program for different interplay between neural and symbolic. So this is, again, based on the older ideas that we had, and I think it's still applicable when thinking about an integrative paradigm for the AI systems. We want to have abstractions that are independent from computations. If algorithm 1 is or algorithm 2 is running, I don't need to have the details of the algorithm in my program. I have to be independent from the computations. My design should be independent from that. So we need abstraction that facilitates the algorithmic coverage. We need abstraction that help closing the loop between data and knowledge. How we can really say, okay, this is the data for learning. Now I learned this. This is a piece of knowledge. I want to store it. I want to put it in the memory because this is generic, and I want to build on top of it or use it symbolically. So I think these transitions is very important. So we want kind of possible abstract us to go back and forth between data and knowledge, and then abstraction that help to learn programs. Can we generalize abstractions that actually we can go beyond and learn them like meta learning to have these programs that in those abstractions. So thinking about the languages that actually help us to do this kind of programming, neurosymbolic programming, we were thinking about, okay, maybe we need 3 types of sub-languages here in such a framework. For example, we need to have a data representation language. We have data, and the data is very important. It's going to feed all our neural models, right? So declaring the data and the structure of the data is very important. Maybe graph declaration, nodes and edges and properties is one language here to explain the data. We need a language for knowledge representation. This is when we want to go beyond the data and the structure of the data. So graphs are not kind of expressive enough to talk about constraints, first order logical expressions, second order relationships, or this is soft constraint, or that is hard constraint. So the data representation doesn't have capacity to express this kind of information. So we need to have knowledge representation to be able to express our symbolic knowledge. And as I mentioned throughout the previous slides, we have multiple models, they communicate with each other. And we need a design language that actually help us to program for the type of the communication. Is that a pipeline that the first model gives an input to the second model and the second model to the third and so on? Is this an ensemble? Every model is doing the same small part of the task, and then we're going to combine. Is that a joint decision making? So basically, we need a language that actually help us to be able just design the model configuration in an intuitive way. Now, based on our domain knowledge or the way that we want this to be executed. So here, again, this is an integration framework, a system level. I added this term agentic snapshot that I was designing like kind of 6 years ago for this ONR Office of Naval Research project. I think we have in this agentic framework or system level snapshot, we have dealing with data. So we have more sensory form, and we have this component to program or represent our data. Then we have this knowledge in the middle. We have the knowledge that needs to be translated to actionable knowledge. I need to do symbolic processing on this knowledge. For example, I need to map it to first order logical expression. So we have, this can come from different resources, even text, image, but this is now translated to structured knowledge. And then I'm going to use this knowledge and data. And then I have the model configuration that is going to tell me, okay, you configure your model the way that you communicate, you feed the data, you feed the knowledge, and learning and reasoning happens here. And now this was actually agentic, because the final decision is going to get back to agents. In this design, we meant human agents, that actually the final decision has a problem. Human is going to like kind of redesign the model configuration, or human is going to add another piece of knowledge, or human is going to change the data structure or add another piece of information. But actually in the new agentic frameworks, these agents can be even large language models, that they can generate data, they can map sensory data to more formal knowledge for us. So that's why, I mean, this is the feedback to data and knowledge. That's why I'm going to say that, okay, now with the current technology, we can use language models in all of these components of this whole integrated framework to be able to solve the problems with tool calling symbolic solvers and everything, or translation of the sensory data to more structures that we can actually work with. So then we had this recent paper that actually was the title of my talk today, that, okay, now that is the more broader or more general way of thinking about integrated AI systems. And then that could cover language models, classical models, and everything. I tried to give you more perspective. But here in this paper, we had a more focus on the existing systems and existing neurosymbolic systems. And we picked a few. You can see the paper is archived. You can see the details there. But we picked a few of these systems, and we tried to actually showcase how they like show a specific problem, what are the algorithms that they are using for solving. Do they have, is this a specific algorithm? Is this a framework? So we try to actually discuss these issues in this paper. And here is a bit kind of more focused framework that it can be based on what I discussed so far, that usually in the neuro-symbolic frameworks, we have the symbolic reasoning part, we have the neural reasoning part, and we have the interplay between symbolic and neural. And this is basically the six kind of combinations of Henry codes that we put here just as a showcasing of what we mean here by interplay. But then we also looked at a few of these examples. Dominoes, of course, I'm going to self-promote here. This is a framework that we designed in my lab the last 5 years. And then there was also great other frameworks that Deep Problem is much older, like is based on much older Problem ideas and extended to deep learning. Scallop was kind of afterwards. I think it built somehow based on Deep Problem ideas, but implementation in different way. The logical component is different. I will tell you a little bit more about this. But in the paper, we try to look at these three frameworks and show how they express a specific problem, what are their efficiency, and so on. So we have a few examples in that paper. You can take a look at the details. In the paper, in the appendix also, one of the examples that we were looking at, it was simple MNIST sum example. This example is very simple, but also very interesting because it shows how the neural modeling and explicit computations needs to be combined. The example is as follows. You have input like digits. You see the images of 2 and 5 here. So a neural model can do digit recognition, but actually I want the data that I have has the input of pairs of digits and the output of the sum of them. So basically I say 2, 5, and then 7, or 3, 5, and then 8. So that is my data. I have pairs of digits in image form, and I have the final summation of those two digits. And I want to learn from this information to actually do the digit recognition. And also my system needs to give me the summation when I give it 2 digits. I want the system to give me the summation correctly, but also I expect the model to do the digit recognition meanwhile, right? So this is basically, again, similar to the counting problem. I don't want you to just look at these numbers and tell me the summation by memory. I want you to do the actual summation, because then I can rely on your computation. So here is the example that is taken from the Scallop Forks slide that shows how the models possibly can learn the probability of every specific digit. So basically, if I have 2 here, I get a neural model, gives me probability distribution of 0.2%, this is 0, and 87%, this is 2. And here again, I have like 0.2%, this is 4, and 88%, this is 5. And then you get the values and their probabilities, and you do the summation in a kind of probabilistic logical probabilistic way of doing it. And then you get me the probability of, okay, being 7, and most probable is 7 here. So this is basically what we want happen. But this box of a Scallop is like how the models do it, how the neural information is combined with the explicit logic is the key point of the kind of neurosymbolic systems and how they implement this idea. So just briefly talking about the Scallop. In a Scallop is basically the logic is taken care of by description logic. It's data log. So data log is, again, I showed you in my list of database systems with deductive reasoning. So data log is, I think, the most famous one, or more kind of application level one that was designed. And it is able to do logical reasoning. We can have databases, relational data, and the deductive reasoning on top of it. They use that engine, but they combine it with the neural modeling. Here is a snapshot of the one. It's not all the code here. It is high-level code that does the image, neural image recognition here, like MNIST network. This is a neural network that gets the image A, image B, and there is a sum tool that is going to get the probability distribution of image 1 to the probability distribution of image 2, get the summation, probabilistic summation, in a way that the probabilistic reasoning is done in a Scallop, and then give me the most probable answer here. So there are other frameworks like Deep Problem doing the same thing in a different way. So as I mentioned, Scallop does it based on data log, but Deep Problem is doing it based on the prolog and its probabilistic version problog. So you see the prolog lines, you have again digit X and Y, and then you have this neural model is going to actually get this like prolog rules, and then addition of x, y, z is digit x, y, and x2, digit y and y2, and then z is x2 plus y2. This is pure prolog coding, but then you have the probabilities that are coming from the neural side, and then the composition of this probability distribution is done based on the prolog resolution trees, and again mapping them to some differentiable like kind of operations like max, mean, or and or, and then they can actually have this differentiable resolution that is differentiable, and you can get the answer to the sum and back propagate the error and tune the underlying neural models for digit recognition. So the sum is done explicitly based on the probability distributions, and the errors back propagated to the digit recognition that gives me better and better probability distribution for recognizing the digits, which strengthens the neural part based on the symbolic supervision. We can explain it like that as well. So Deep Problem, Scallop, and in Dominoes, I wanted to also tell you, if we have a little bit of time, a little bit more about Dominoes. So as I mentioned, some of these frameworks, one of the characteristics of this framework that I wanted to highlight is that you start from a specific formalism like prolog or data log, and then you build around it, you extend the predicates to be neural and give you probability distributions. But how about we don't stick to the specific formalisms, and we start just writing based on, okay, these concepts that are Python concepts, and we want to connect them to neural models. We want to write the logic without even like having a specific logical formalism underlying it. And then how about really connecting to a specific solvers when needed and depending on the type of reasoning that we need. So that is basically the wish for having Dominoes, to not starting from a specific symbolic formalism and extend it to neural, but start writing the program declaratively based on the domain concept relations and logic that we want, and then try to extend this to cover different types of algorithms and reasoning systems. So that is the wish, but it has its own challenges, of course. So again, you can look at the paper for the details of comparison. We also have some aspect like, okay, how the symbolic representation in these frameworks work, how the interplay is designed, and if they use also large language models in each framework. This is also kind of just to point to some of them. In Dominoes, we don't have any specific formalism or language that you have to learn to write the program. You don't need to know Prolog, or you don't need to know Datalog. But you in Deep Problem, you have to know that language. In Scallop, you need to know that language because the queries are passed to that kind of specific engine at the end. And that is what we want to alleviate. I mean, ideally, you might look at it as a strength, but actually, I think for the next generation of Neuro-Symbolic, I see it as a weakness that actually bounds us to a specific formalism. But then we have the knowledge representation language. Also, I wanted to explain that sometimes we have algorithms for integration of neural and symbolic, and the algorithm doesn't talk about how you represent the logic or what you do. It's actually a specific algorithm. If you have this and then I use it in this way or that one. So I don't call them generic frameworks or generic neurosymbolic frameworks. I just call them algorithms. I think, as I discussed over this last hour, I think an important aspect of neurosymbolic frameworks is that you need to explicitly write the logic in your program in this framework. And the knowledge representation needs to be handled in the framework. Like, again, going back, Diprolog uses the prolog to use this to represent this knowledge. Datalog uses the Scallop uses Datalog to express this knowledge. So I think I call these frameworks because I think they have this knowledge representation there. And dominoes, we are not bounded, but we have this knowledge representation also as in a kind of explicit way in writing the program. Is not something behind scene that I'm going to handle it in an algorithmic way and like attached to my or entangled with my algorithm. Is something that is disentangled, is a representation that can be interpreted and used later in the algorithm. So that is I think a component that is needed in the generic frameworks. And then we can have multiple algorithms to be covered. Again, pointing to dominoes, we have different kind of sampling or dual formulation using the logic as a loss term in a loss function, or having executable logic that can be differentiable. So we are having these components in dominoes. Diprolog and the Scallop, they are having this logical resolution that is extended to its own probabilistic way of doing it. And then the resolution trees are mapped to differentiable operations for logical reasoning. That is also an algorithm that these frameworks, both of them follow, though Scallop has its more efficient way of implementing it by taking top case solutions and so on. So some efficiency considerations are here related to the underlying algorithm, as well as the kind of efficiency of Datalog itself. So yeah, let's move on from this. We have also some report for the execution time of these frameworks, depends on the task and the representation that they take for each task. Sometimes you have to represent the task in a way that the framework is able to solve it, and that might make the solution to take more time. For example, MNIST-SUM, you see that Diprolog actually does it quicker than a Scallop, though we expected Scallop to be more efficient from the algorithmic perspective. Dominoes does it a bit less efficient because we have all this graph that is generated in the memory and makes the training a bit slow. But at the test time, Dominoes is fast because you just have one instance of the example, and then you can answer it quickly. We have the memory track of these systems, and we do this for different kind of toy tasks. Like this is entity relation extraction, so name entity recognition, NLP task, MNIST-SUM. Math inference, we have also like bunch of list of numbers, and we have different mathematical operations, and we want the model to learn to do those operations on the lists of numbers. We also report this numbers here, or visual question answering with like given an image and a question, you want to answer the question in a symbolic way. That is also we see that here also, like there are Scallop is more efficient here in solving this problem. So this is about I had a slide about Diprolog here, but also, do I have time? Can I still take a couple of more minutes? I assume yes. So I'm going to also, like again, as to do a little bit of self-promote about Dominoes here. In Dominoes, we have the backbone is deep learning libraries. As I mentioned, we have this symbolic representation, which is invented in Python language. And the logical expression is not bounded to any specific logical formalism. It's basically invented Python expressions to express the logic. And then we connect the elements of our graph to the deep learning modules that could be simple multi-layer perceptrons or large language models. Whatever neural module that can give me probability distribution can be connected to my symbols. And then I can have my logical expressions and then can connect to different kind of ways of computing the logic or using the logic as constraints or as a program execution in a hard or soft form, and then use different variety of algorithms to solve these problems. I think due to the time, I'm going to skip this slide. Just my goal of this slide was that to show how we can get probabilities for each concept, and then this is an entity relation extraction problem that you say, okay, Washington works for Associated Press or covers Seattle for Associated Press. Then we want to see the probabilities of this being a person, this being a location or organization, and this relationship being employed by or work for. And we want to apply type constraints on the extraction of the models. Let's say people can kill people, but people can work for organization, but maybe people cannot work for people. So we have these type constraints that we want to impose. This was the original idea of dominoes, that we want to do constraints with deep learning, and later we extended to other paradigms. But here the constraints actually are mapped to some integer linear programming, and we get the best solution subject to constraint in this case. So due to the time, I'm going to skip this. What I wanted to say about domino is, like, we have different type of training time algorithms that use the logic, inference time algorithms that can use the logic as constraint, and inference time algorithms that can actually execute the program, and inference time algorithm that can execute the program and backpropagate the errors. So these are all covered in this framework. This is just a piece of code that shows you how we define concepts and relationships in dominoes and the constraints. Also, something that I wanted to mention is that now, thanks to the large models, actually using Neuro-Symbolic becomes much more feasible than before, because we can use like language models to map to sensory data to some formal representations, that we can correct it with the symbolic solvers and interaction loops. So here we actually have an agentic framework in dominoes that can help us to actually write the program, write the logic with an agentic framework, going back and forth, having the user in the loop, correcting the program, correcting the graph, and then try to make the knowledge declaration, model declaration, composition, and everything, and get the Python notebook at the end that actually has the program itself, the whole program, in an agentic framework. So we also have this kind of reviewers and code generation, visualization of the graph and everything. I just got a snapshot from the web application that we have provided. This is a very recent work, and I can share the link with people to try it. This is my last slide. I just wanted to say that, okay, these questions are designed, I think, about many years ago, like 6 years ago or maybe earlier. But I think these questions still are valid. When we want to design general frameworks for AI systems for solving complex problems, we always need to think about these questions. What is needed to be expressed in the program? What is the abstraction that we want, how we show the uncertainty, how we show knowledge, how we show data. Is this a language that starts from compiling, or is this a high-level library? These are still, I think, valid questions to ask. Thank you very much. I'm open to questions.
Okay, thanks so much, Parisa.
You're welcome.
There was just from the chat and on YouTube, was a discussion about where to learn about these kinds of things. So as I was mentioning at the beginning, Parisa is actually a part of our education committee, and you'll be seeing our version, at least, of a guide to Neurosymbolic AI. It'll appear on our learning site that we gave the link to at the beginning. So you'll see that. It's on the Centaur website. It will be on the Centaur website. So we'll hopefully provide the community a good answer to that question. How the heck do you learn about Neurosymbolic AI? So, but Parisa has also given us in this talk, you could say, a good step for that, because these frameworks are sort of very important, because they're sort of trying to lay out the landscape of the problems you can solve, and how different pieces interact with symbolic pieces. So by looking at these frameworks, I think this is a big part of understanding how different approaches are trying to achieve neurosymbolic AI. So any questions, Olga?
Yes, we do have a couple of questions. So first one is actually a comment. I'll read it through just in case if Parisa has anything to say about it. So the comment is, I have seen some interesting work from Pedro Domingos. One second. From Pedro Domingos with regards to tensor logic. And in addition, geometric deep learning, which can bridge both neural and symbolic. This is just a comment.
Oh, sorry, I haven't cited that. Sorry for that. Yeah, but I think I was referring to the Markov logic networks, which is older, and TensorFlow. I mean, I didn't cover all of the frameworks. I just gave examples. Yeah, sorry for that.
Okay, the next question, actually, Alex partially answered this one, but just in case if Parisa, you have something to add, I'll read the question. For someone getting started on neurosymbolic area, what framework is suggested? I am very familiar and have expertise in deep learning, generative AI, machine learning, but looking for ways to bridge.
Yeah, I think this is a hard question. I think the framework that I showed, like Scallop, DeepRoblock, or Dominoes, they are following different kind of, I mean, maybe Dominoes is a bit a different school of thought, but I think all of these can be a kind of, for warming up, looking at multiple systems, I would say would be great. And then when you go to very serious kind of complex real world application, you might even, for any of these, you might see the limitations, because these are, that is the problem. These are developed at the academic scale. So, and then it's not that like, okay, PyTorch has been so many people behind it, or like, with APIs for the large language models or Hugging Face, there are so many people behind it that is very well developed and it's ready to go and use. That is the challenge that I want to show here. We don't have such a ready to go, to my opinion. Maybe people have objections here, but to my opinion, we don't have something ready off the shelf that works for any complex problem that you want to solve. Even in my framework, I can speak from Dominoes. We do a lot of toy examples. We do some complex examples, but whenever we want to solve a new problem, we add features to our framework. And we have been trying also other frameworks that I mentioned some of them here. And we see the same issue. Whenever we want to do some new problem, we see there is a hassle to really get it done in the current framework. So I think if you're interested, you need to try different models to get a sense of what can be done, what not, and sense the limitations deeply. And then maybe I hope that more people come up with new ideas and more resources allocated to develop more sophisticated, user-ready frameworks. That is what I can say. Sorry.
Yeah, thank you. Okay, the next question. Do current neurosymbolic frameworks support large-scale vision tasks with out-of-distribution robustness? And can they leverage LLM agents and causal discovery for more reliable, explainable predictions?
I don't think the frameworks necessarily do that. There are different works at the algorithmic level. Okay, let me do this for causal discovery, and let me do this for addressing this vision problem with a specific, not generic setting. But for example, let's say for vision problems, we have visual question answering, and we're building a framework. Okay, go from the questions to formal representation, and then get basically the differentiable program execution and solve this vision problem. Left was the one of this framework that was designed for this, but it's very specific algorithm and specific pipeline that it follows. But then we are trying to do this in a more generic way in Dominoes, that if you have the task specification, or if it is instance-based inference, how you can switch between the higher level knowledge and low level knowledge about the specific example and task. I think there are efforts, like Scallop does this LLM based, has this one. It deals with some toy examples on VQA. In Dominoes, we have these toy examples and we solve some of these problems. But again, I don't think I can say like generic frameworks deal with this problem in a generic way. I don't think any of them can do that.
Okay, thank you. The next question is, should we use knowledge in a neurosymbolic framework during training or during testing, or is it task dependent? If during training, may it overfit our model?
This is an easier question. I can answer that. I think if we have knowledge and we can use it during the training, usually this means we use it in a kind of neural way of doing it. At the end, we train a neural model when the knowledge is used during the training. But then we hope that our supervision from the knowledge, depending on the way that we use it, helps the model to capture the higher level patterns of reasoning based on that knowledge. And then this will hopefully alleviate the need for using that knowledge during the test time for the tasks that we need them to be real time and efficient, right? So basically, I think depending on the task and situation and application, we can use it during the training. Then we get the gains for more efficient inference. But if we are having safety critical problems that is very sensitive, I don't want to hit the wall. I'm doing like using the self-driving car. So I really want this constraint to be hard. I don't want to pass the like red light. So I'm going to impose the logical constraints or domain knowledge constraints explicitly at the inference time. So that might add a little bit of latency, but I mean, again, that is where we want to use them, certainly during the inference.
Mm-hmm. Thank you. The next question is, just wondering if I understood correctly, the knowledge in neural structure is spread across the neural net topology. The framework presented aims to represent chunks of the topology as graphs?
Oh, no. This is, I mean, there are like systems that design the logic in the architecture. But here we don't have this. Here we actually have it at the higher level. We assume that architectures could be black box, and they are going to serve as perception level. They give us distribution about the concepts, and all the reasoning and logic and everything is applied afterwards. So we can compose the output or distributions coming from the perception level and combining them at the reasoning. I think this is the case for all the three systems that I showed. So in Dominoes, we have this. In Problog and Scallop also, they have the neural module that gives me the probabilities. I can go back and tune the neural module, but the architecture, I'm architecture agnostic. Whatever can give me probability, I can use the output. And I'm not going to interfere in the design of the architecture. But there are other techniques. I think, for example, the CNN Plus has one layer that is added on top of the neural network that tries to impose the logic with a specific additional layer. And there are other also techniques that they try to do and or gates in the design of the architecture. But the examples that I showed you mostly are kind of underlying architecture is a black box. I just use it for composition externally.
Mm-hmm. Thank you. The next question is probably a follow-up from some previous questions. Which framework is the best choice for researchers?
This is a hard question. As I mentioned, for research, I think people should look at multiple frameworks. Yeah, that is my suggestion. I think we try to do the, in terms of documentation and being generic, I think Scallop is doing a good job. The Problog is doing a good job. And in Dominoes, we're trying to actually document this as much as possible and cover different types of algorithms. But I think for research purposes, people should look at multiple frameworks. And none of these frameworks will solve the research problems for you but I think there is a potential here to add to the existing frameworks when you do research in this area. One thing that I wanted to, again, self-promote is that for Dominoes, we wanted to really push this idea that I'm independent from the algorithms and it's easy to integrate different algorithms. So that might be a good capacity for actually extending the framework more easily. That is one thing that I can say, but yeah, it's not really a kind of industry level software that is easy to use.
Thank you. Okay, next is a comment. Paris, I really appreciate your perspective and explaining the potential for production application with current frameworks. Thanks. Okay.
What was the question?
There is just a comment, not a question.
Thank you so much. Okay.
Yeah. And okay, next is a question. Would you have a recommendation of a framework amongst the ones you presented? We can start with if we are looking for the starting at the current frontier of research.
I mean, it's hard for me to say, okay, use Dominoes because I'm developing that. But I think Scallop I liked as well. So you can look at Scallop and Dominoes. Deep Prolog also is great, but maybe it's more bounded to Prolog and kind of maybe less efficient. Yeah.
Mm-hmm. Okay.
I mean, from the application perspective, I'm talking about, but those frameworks have really beautiful theories and formalisms behind them.
Thank you. And I think the last question, how would you classify the research areas, assuming that different frameworks and algorithms work best for each?
With application problems in general, like which algorithms, I think that is a very difficult question, right? We cannot say based on application which algorithm is the best. I think for the many real world problems, like, okay, domains like science, maybe I can say this, like in scientific kind of discovery or problems that we have formulas like physics, chemistry. I think if we can really have this explicit integration of the knowledge in learning, those are really obviously those are the things that we need. For problems that have more perception, like vision, language, maybe you don't have really very explicit like rules or common sense is hard to kind of make reasoning over the common sense like formally is a bit harder. So for those applications, maybe the language models can help us to, based on the situation, get some formal knowledge based on the situation and integrate it. So it depends really on the application. It's hard to give like general statements, but some domains you are more structured. Like again, legal reasoning, that is something that I'm looking into recently. I think there has been a wish to do prologue reasoning with the rules of law. And it has been very difficult to do this in the past because mapping to prologue has been so hard with semantic parsing, classical, traditional semantic parsing. But nowadays with language models, you can tune, you can give prompt engineering, you can do step-by-step reasoning of mapping to these formal representations. And I think it has been much more feasible now to do, for example, legal reasoning with LLMs and mapping to formal. So some, again, sorry for repeating myself, some domains are more structured. There is explicit knowledge that can be used off the shelf, like math, physics. Sometimes there are some rules that, again, like legal domain, you can map with language models to formal, and then you can use them. There are domains that maybe the knowledge is not clear, but even the language model can help you to get the world knowledge and then also map it to formal in a kind of agentic frameworks with back and forth and tuning human in the loop, and then solve those problems. Yeah. We cannot comment at the very low level algorithmic. I think it is hard to even say anything like this algorithm is good for that or something like that.
Mm-hmm. Thank you. A couple more questions appeared. It seems like there is a lot of human effort required to bring neural models towards effective integration with symbolic models, be it through annotated data training, RLHF, etc. What do you think?
Actually, I don't think so anymore. I think maybe like maybe 20 years ago or even 5 years ago we were thinking like that, but that is the main point. I think with the like kind of with the large scale usage of large scale training that we have with neural models nowadays, actually we have a platform that we can now exploit the symbolic reasoning much better by using the neural models, give us the formalisms, right? Give us the translation to formal representations. For example, in our recent work, like with visual question answering and referring expressions, we actually don't need to come up with domain predicates. So that was a bottleneck in logical reasoning, right? Classical AI. You have to start with ontology of the domain. I have these 5 concepts, have these 5 relations, and these are the rules between them. You don't have that, you cannot do any symbolic. And if one concept is added or missing, then you have problems. But nowadays, we can use the large language models to get actually these predicates with the help of these models. They are exposed to the billions of elements of data in the real world, and they can actually help us to get the domain predicates on the fly and use them and pass them to the logical reasoners that can give us robust and reliable solutions. So I think these two systems hand to hand nowadays actually is really good. And thinking about again efficiency, I don't think those classical efficiency problems in the way that I see them exist anymore. If I'm thinking about again neurosymbolic and hybrid systems, and I do per case reasoning, if I'm going to do logical reasoning over 5 predicates for solving this specific problem, calling Prolog, that doesn't take me more than calling like autoregressive reasoning model. The autoregressive reasoning model can even take more compute and time compared to calling a solver, because we are thinking at a different level per case and solving a specific problem at each time.
Let me I want to spend some time on dominoes. I think it's to me a very powerful idea that you're espousing there, to sort of make the logic choice invisible, or maybe you have a better way of stating it, but so that you don't really have to come with being an expert in some particular logic, say. So I think that is a very important goal that we should have. So if it can be achieved, and also maybe your bigger vision about framing all of these things as declarative learning based synthesis. So I think meaning automate more, less. I take this to mean overall require less kind of upfront specification and learning of formal languages and so on. So I think this is important for the success of a neurosymbolic, or really the symbolic side of neurosymbolic. So
Totally agree.
now what just to comment on that a little bit. So you showed we go into that a little bit. You showed the MNIST sum task, which, by the way, for our audience, you'll be seeing that again. This is sort of emerged as our the classic now neurosymbolic problem. Which part, or maybe you said this already, but maybe we could review it. Which part of that is learned when you approach that with dominoes? Which part do you have to specify, and which part kind of do you not have to specify?
I think we can have different in dominoes. We can design differently. You can actually just have it neurally depending on how you write the program, and get supervision from the output, and then you have these concepts that they pass their representations concatenated, and then the sum. But we don't want this, right? This is possible, but we want the actual sum to be done but taking the probabilities into account. So I have the probability of this number, this digit being 1 is 20%, and the other being 2 is 30%. Now the probability of the sum being like 2 plus 3, then it's 5. It's 20% multiplied by 30%, if I remember the numbers that I mentioned myself. So basically, I get the probability of the sum. I do actual sum, but then I get the actual sum, and then the probability of that summation is the probability of the input digits of that. Then I can compute and then so then in this way I can compute the most probable summation of these two digits, and then backpropagate the error through that, because I'm dealing with the probability, so I can backpropagate the errors. So I think that is somehow something that happens in the other two frameworks as well, but representations are different, because in Prolog, you actually have the actual expression that says this plus this, that, and then you just have the logical program with the underlying neural models. In Dominoes, we have to define the concept as a graph, and then define the logic, and then define the type of algorithm that we are calling there. In a Scallop, it does the same thing, but it calls again the data log for expressions. It passes the data log expressions to the underlying data log engine to do this probabilistic summation, I would say. This is the way that it's working. But in Dominoes, we have to try different ways actually to solve this, like end-to-end, or getting just the distributions, concat them, and then do the neural learning, or do the actual summation with the different possibilities and use the probabilities to backpropagate the error.
So yeah, I want to really highlight, or at least in my opinion, working on and developing a framework like these that Parisa has told us about. Very, very important part of the success of Neurosymbolic AI. So we're never finished. Of course, each successive framework sort of learns from previous ones and so on. But tell us about open challenges in your opinion. So you mentioned scaling up kind of to industry scale, and part of that is sheer resources. But you could say a model could be what's happening in LLMs, which clearly there's a lot of resources, a lot of commercial interest. So what can we learn or from the frameworks that have emerged around LLMs and deep learning to take into Neurosymbolic, or not learn, as in maybe certain things just emerged, but they weren't that great? What would you say? Because one observation I want to, you mentioned PyTorch, of course, crucial part of the whole success of deep learning, and LangChain, and now MCP and other things. But some parts of it they're not really done. There's so much to the ecosystem that some things are just completely done separately by separate groups. Like, well, the reinforcement learning stuff is, RLGym, whatever, that's done by other people, and RAG and MCP by different people. So what would you say we should learn or not learn from deep learning ecosystem?
I think actually we can learn a lot, and we can think about neurosymbolic like modeling as a kind of, as I mentioned, I was trying to like push that idea that this could be a neurosymbolic framework. A general neurosymbolic framework is actually an agentic frameworks with the ideas that I had from declarative learning-based programming and so on. We have different models. Now we call them agents, and they are LLMs, right? But we can have different learning models that communicate with each other and solve a task together. We have some logic going on between this output of these models to be able to solve the final problem. Now, in the agentic frameworks, the communication is not formalized. It's more like raw data communication, raw data learning. There is tool calling, but the tool calling is not like kind of integrated in a principal way of, okay, now I have this differentiability of logic, for example, in my tool, and my tool can be actually a hybrid neurosymbolic way of doing it. So I think actually we can take this, because this is a kind of, okay, there is a large community behind this, there is a hype, and a lot of young people are interested in this like a new way of doing things in the agentic framework. But I think we can actually take that kind of infrastructure and say, okay, how I can make this a more principled way of doing neurosymbolic for agent communication, for logical, different kinds of logical reasoning, and so on. So that is, I think, will be very interesting. Yeah. If I answered your question, I don't know. You see.
Well, no, it's open-ended. But and at least one challenge I'll translate from what you said is unifying, the ability to unify between different sort of sub-frameworks, if you will, like probabilistic graphical models versus neural nets and so on. By the way, thanks for mentioning AutoBayes, which I worked on with Ray Bunty. But that seems difficult. But would you say that's one of the things we should be aiming for, or would you highlight some other things as sort of targets, open problems that we should be addressing when we're thinking about new frameworks?
Yeah, I see. I mean, it's kind of when I'm thinking about black box tool calling now that happens in the like agentic frameworks. I think if the neurosymbolic people are in a good situation, that actually they can adapt every kind of reasoning tool in a principled way in this kind of framework. Maybe I can rephrase what I mentioned like this. For example, let's say if like deep prologue is integrating, let's say, prologue kind of reasoning with probabilities and connecting this to deep neural models, generated distributions, right? So now, let's say we have, I mean, this is again going back, it becomes a very fundamental problem of like how we can have a unified logic that we never can have, right, classically. But again, if we stay with the current technology in the symbolic side, maybe integration of this kind of symbolic reasoning in a more principled way in these agentic frameworks for translation, differentiable execution, and so on, or inference time, training time, different configurations. If we can actually, we can leverage the current agentic frameworks with these logical systems, and being able to switch between the type of logic that is needed for reasoning, that might be, I think, very interesting, at least kind of maybe next step that we can leverage the neurosymbolic reasoning.
Okay, multiple types of logics. Okay, well, we're at time, and I think we still have some more questions. It's at least one more on Discord, but we won't have time. But Parisa, if you have time, maybe jump on Discord and can maybe answer any remaining questions. Otherwise, I will put out the slides we showed at the beginning, so you can contact Parisa, and you should check out Dominoes and check out the other frameworks as well. We'll have people talking about these various things as we go on. And we'll hopefully have Parisa help us with the new agentic setup where we mentioned. All right. Well, thanks again, Parisa. Thanks, Olga. Thanks, everyone.
Thank you for having me. Yeah, see you.
Take care.
Thank you very much for having me.